Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, I'll start. Thanks for coming on the eve of the Sera. Yeah, we did not realize it was going to be eve of the Sera today. Okay, so I'll talk about some algorithmic problems in high dimensions. Most of you have seen things in high dimensions, but let me remind you of a few things. So we are all familiar with two-dimensional space and three-dimensional space. The point in two-dimensional space is specified by a tuple of 2 points, in three-dimensional space by 3 points, a tuple of 3 points. And in general, we can talk about n-dimensional space where a point is specified by a tuple of n points. So we can visualize things in 2 and 3 dimensions, but higher dimensions is harder to visualize because our physical world is three-dimensional as far as we can see. But many things generalize very easily in n dimensions, like the length of a vector or addition of vectors, they all generalize in easy way. Also familiar shapes like squares or cubes, they have higher dimensional counterparts. So higher dimensional cube can be specified that way. Maximum of the absolute value of x1, x2, xn, the n coordinates at most 1. That gives you one particular cube. Similarly, the ball is given by that equation. Triangle with three-dimensional counterpart is tetrahedron. In general, it's simplex in n dimensions. So that can also be generalized. The parameterization is a little bit more complex, so I haven't shown it. So many things are just like what you expect them to be. So let me just give you a definition of what I mean by convex bodies, although most of you probably already know. So we say that a set S in Rn is convex if for any 2 points P and Q in the set S, if you join them by a straight line segment, then all points on the segment are inside the set. And we say that the set is a convex body if it's a bounded set. It does not go to infinity in any direction. So the set on the left, this is convex, but this is not convex because this line goes outside the set. Okay. So in this talk, we'll be interested in talking about volumes of convex bodies. So let me define what I mean by that. So one definition of volume could be given like this. You take a grid formed by squares of size t by t, and then you look at which squares are completely inside the body. You count them. So number of squares which are in the body, multiply them by the volume of the square, which is t squared. And that gives you an approximation of the area in 2 dimensions. And as t goes to 0, this approximations becomes better and better, and in the limit, it gives you the volume. In higher dimensions, it's the same thing. You take a grid, which is formed now by cubes with each side of length t. And the volume is the number of cubes which are in the body times the volume of the cube. And again, in the limit, it gives you the volume exactly. So this already gives us some interesting properties, interesting phenomena which happen in high dimensions but not in small dimensions. So if you double the size of a body in the plane, you increase every dimension by 2. Then the volume or the area in 2 dimensions multiplies by 4, factor of 4. In n dimensions, it multiplies by a factor of 2 to the n. Okay, that's easy enough. And this leads to this quite counterintuitive phenomenon, which is if you take a convex body in n dimensions, then most of the volume of this body is near the boundary. And we can see that very easily. So if, let's say this is the outside body, this is the given body, and we shrink it a little bit just by a factor of 99 over 100, by a factor of 1 minus 1 over 100. Okay? K is the body which is the outside body. This is K. We shrink it a little bit. Then the volume scales by this factor, 1 minus 1 over 100 to the n. We scale the body by a factor of 1 minus 1 over 100. Volume scales by the same factor raised to power n. And so it's a very small number. This is exponentially small in n. So just by shrinking it a little bit, the new body is very small. So most of the volume is actually here in the boundary, which you can't see in 2 dimensions, but that's what happens in high dimensions. Okay. So there are many such phenomena which happen in high dimensions, and they can give us new algorithmic challenges. So there are many algorithmic problems that we study in high dimensions, in machine learning, in data structures, in optimization. So, and they change characters many times when we go to high dimensions. So for example, nearest neighbors problem, where you're given a couple of points, you store in a database, you're given a new query point, and you want to know which point in the database is closest to the query point. It becomes much harder when you go to high dimensions. Either your database has to be very large, or your query time has to be very large. But there are also some useful features that we can utilize in high dimensions, like the central limit theorem. And using these features, we can sometimes reduce dimensions. So if you are satisfied with approximation, the nearest neighbor problem, then we can get relatively efficient data structures by reducing the dimensions. But today I'm going to talk about some problems that involve convex bodies. Not about nearest neighbors, not about optimization, but I'll talk about these 2 problems. Estimate the volume of a convex body, and can you learn a convex body? There are many other problems people study, like optimization of a convex body. Linear programming is a special case. But I'll just focus on these 2. Okay, so what do I mean by estimating the volume of a convex body? We have to first talk about how is the convex body given to us. Okay. So some familiar examples of convex bodies are convex hull of points. So you're given some set of points, take the convex hull. That's a convex body. There is intersection of half spaces. You're given some half spaces like this. So every point in this direction is in the half space, and similarly you have these 4 half spaces, and their intersection is this area. So these half spaces can be specified by linear inequalities, and you can check whether a given point satisfies all of them or not. So in a similar way, you can define many other convex bodies which arise in practice. And many of them are captured by this simple abstraction of membership oracle. Certainly these 2 are captured by this. So we assume that there is an oracle associated with the body K, and we can give a point P to this oracle, and it will tell us whether that point is in the body or not. Okay. So in particular, we can easily construct such an oracle in this case. If you are given linear inequalities for each of the half spaces, we just check whether the point satisfies all of them. If it does, then it's in the body. If it does not satisfy all of them, then it's not in the body. You can do similar thing here, but it's a little more complicated. You have to solve a linear program to answer this query, but you can still do it efficiently. So we'll assume that the body is given by this membership oracle. So now the question becomes this. So we're given a convex body K in Rn via membership oracle. We want to estimate its volume within some multiplicative factor, 1 plus minus epsilon. Epsilon is a small constant like 0.01. So the question is, how many queries do we need to make to the oracle to answer this question? And how much time do we need? So we need to make some more technical assumptions in order to make this problem interesting. So we'll make one assumption, which is there are concentric inner and outer balls. So there's a ball of radius 1, so this ball, whose center is at the origin, which is completely inside the body. And there's another ball whose radius is polynomial in n, and which completely contains the body. So we make these assumptions because otherwise some pathological examples can arise, because the body could be somewhere far away in the space and we don't know where it is, and we have to find where the body is. So that's not really the main problem. We want to compute the volume. So to take care of those pathological things, we make these standard assumptions. Okay, so this is the problem we want to solve. Any questions?
So isn't one of those assumptions enough? Just assuming that there is a inner ball centered at the containing ball.
So you also need to make this assumption that the strictly speaking, you're right. Yes, you can do that. This is for convenience, but you do need the inner ball assumption. Yes. We'll also use the outer ball, but it's not really needed. Yeah. Okay, so let's look at some possible algorithms for this problem. So first thing we could try to do to compute the volume is to just use the definition that we gave before. So we make a fine enough grid, count the number of cubes that are inside K, and that will give us an estimate of the volume. Okay. So what is the number of cubes in such a grid? It's a to the n. So by a, I mean number of cubes on one side. Okay. So the total number of cubes is going to be a to the n, which is a very large number, even if a is just 2. In general, we'll need to make a large, but even if a is just 2, it's 2 to the n, and which is very large. We want our algorithm to work in polynomial time in n. Okay, so this approach is ruled out immediately. We can do this in the plane where the number of points here will be like a squared, and will be 2, and then it's feasible. But as n becomes large, this is not feasible. Okay. So in general, it turns out that this is a hard problem if your algorithm is a deterministic algorithm. Okay. So you cannot solve this problem efficiently if your algorithm is deterministic. And here is a simple proof due to Alikesh 1996. So suppose that the input body is a ball, and the algorithm starts making queries. After m queries, suppose this is the situation. There's met some queries, some of them were outside, some of them were inside, and this is all the algorithm knows. So at this point, the algorithm does not know whether the input body was this ball, or was it this convex hull of the queries that turned out to be inside, right? Because whether the input was this ball or it was this convex hull, it would get exactly the same answers for each query because it's deterministic. So it cannot distinguish between these two. If the volumes of these two things were very close, then we are fine. We can just output the volume of either one of them, and that would solve the problem. But now it turns out that the volumes of these two things are really different. So if I'm calling this thing the convex hull PM after m queries, and let's say the number of vertices here is m, then the volume of this polytope, the convex hull, over the volume of the body is at most m over 2 to the n. M is the number of queries. So m is supposed to be a small number, like polynomial in n. Okay. So the volume of those two things is really different. So if we I'll prove why that is the case, but let's assume that for a moment. And so after m queries, we don't know whether the input was this or that. So at whatever output we give, we will at least make an error of 2 to the n over m square root, which is a very large number for either the ball or for the polytope, for the convex hull. Okay, so as long as m is not very large, this is a very large number. So let me show you the proof of why this is the case. which is quite easy. I'll not give you the full proof, but just the idea. So you look at any point here, any of the points, any of the vertex, and look at the line segment joining it to the origin. And you draw a circle, a sphere, with the center at the midpoint of this segment and the appropriate radius, which is at most half of the radius of this whole thing. Okay, so you draw such spheres for each vertex. Then the union of those spheres contains the whole polytope. One can show that. So here, for example, you can see this whole triangle is contained in the two spheres. So in general, if you take all the spheres, then the whole polytope will be contained in that union. And each of these balls has volume at most 1/2 to the n, relative to the volume of this full ball, because its radius is at most half. Okay. And since there are at most m of these balls, so the volume of this whole convex hull is at most m/2 to the n, relative to this whole ball. So you cannot do it if you are working with deterministic algorithms. Okay. So what can we do? So before proceeding, I want to just give you a very simple problem which sort of gives you an idea of what's going on in our setting. So this is very high-level analogy, and of course the volume problem is much more complex, but something similar is happening here and there. Suppose we have a very large array of size 2 to the n, whose entries are either 0 or 1. Each entry is either 0 or 1. And we want to estimate the number of ones in this big array. But we can only look at polynomial number of points. Okay. So we cannot do this deterministically, because if we are doing it deterministically, then maybe we always look at zeros, even if there are lots of ones. But if we look at points at random, then we get a good estimate, at least when the number of ones is large. Okay. So the lower bound here is basically what we did before for the volume problem. And this gives us some idea of what we can do. So we can try to do some random sampling for volume problem. Okay.
What does this large mean?
So let's say constant fraction. That's the easiest, or 1/polynomial in n fraction. Then you can just look at some logarithmic log n number of random locations, and that gives you an idea of what the total number of ones is. Okay, so we'll try to use randomization for the volume problem. So what does it mean here? Oops. So by randomization, we mean the algorithm can make random decisions, and with probability at least 3/4, it outputs the correct approximation. It can fail with small probability, but most of the time it gives you the right approximation. So what can we do? The simple method that's very much used in practice in small dimensions is the Monte Carlo method. So if this body is your input body, K, and you want to estimate its volume, then you surround it by some other body, something like some simple body like the cube. And you generate random points in the cube, which is easy to do. Okay. In a cube, you can easily generate random points. And you see how many of them are inside the body and how many are outside the body. And the proportion of these points gives you an estimate of the volume. Okay. But this is not useful for us, because suppose your input body was this ball, and we put a cube outside, then the ratio of the volumes is very small, which is again a very surprising thing. It's 2 pi e over n, which is a very small number, raised to n over 2. So the ball is really like a tiny speck inside the cube. So some people say that this is the right depiction of the ball inside the cube rather than this. Of course, this is not right because it is not convex, but at least shows the right volume. Okay. So since this is very small, so if you are going to do this sampling, then you'll really need to have lots of samples, exponential number of samples to even get a single point inside the ball. So that's too much. So we cannot use random sampling for solving this problem. Okay, so the main problem here is that the idea is sound, except that the volume of this inside body is much smaller compared to the outside body. So here is a nice trick that's used. So none of this is my work. I'll talk about some of my work towards the end. I'll give proper credits in some time. Okay, so to deal with the problem that we saw on the previous slide, we use multi-phase Monte Carlo method. So what is it? We define these convex bodies, Ki, which is the intersection of the input body K with the ball B with origin as its center and radius 2 to the I over n. Okay, I goes from 0 to 10 n log n. So what does this mean? When I is 0, then the radius is 1. So we saw that the body contains a ball of radius 1. So for I equal to 0, this ball is completely inside the body. And when I is large, when I is m, 10 n log n, then this number becomes n to the 10. So we assume that the body is contained in a ball of large radius, polynomial radius, of let's say radius n to the 10. So the last ball here for I equal to m contains the body completely. Okay, so we get this series of balls whose radii are increasing very slowly, and we take the intersection of the body with these balls. Now we can write the volume of K, our input body, in this form. So K0 is just this inner body. And then we have this telescoping product, volume of K1 over volume of K0, volume of K2, volume of K1, and so on. So you see that volume of K1 cancels with volume of K1, volume of K2 cancels with volume of K2, and so on. In the end, what will be left is just volume of Km. Volume of K0 also cancels with volume of K0. And Km is exactly K because the outside ball contains the body completely. Okay, so we get this equality. And now the point is that each of these ratios can be estimated very well. Each of these ratios is between 1 and 2. So I'll not prove this. This is easy to prove, but you can intuitively see this. So if you look at 2 of these balls here, then we are looking at the ratio between the intersection of this inner ball with the body and intersection of the outer ball with the body. And they are not very far from each other. So their ratio is not the ratio of the volume is not too much. So the problem that we had in the previous slide, that the volumes differed a lot, that does not occur here between these any two consecutive bodies. So now we can estimate the ratio, this ratio, provided we can generate a random point inside Ki. So this is the outer body Ki, and this intersection of this inner ball gives you Ki minus 1. We generate a random point inside the outer body and see how many of them lie in the inner body. And that will give us a good estimate of this ratio, because the ratio is not between 1 and 2. But now we have a new problem, which is to generate a random point inside Ki. Earlier we had a cube in which it's very easy to generate a random point, but now it's some irregular shape, something intersection of the ball with this convex body. How do you generate a random point inside? That's the question. All right, so here another kind of Monte Carlo is useful. It's Markov chain Monte Carlo. So now suppose we have a convex body like before, and we want to generate a random point here. So to do that, we set up a Markov chain. If you don't know what Markov chain is, it's okay. I'll just use a very simple version of it. And you run this Markov chain for sufficient number of steps, and after that you will have a random point in the body. So specifically here, the Markov chain is this. So we put a grid of side lengths 1 over n cubed. So each of each of the cube has length 1 over n cubed here. And it starts from a lattice point which is inside the body. So in particular, we know that the origin is in the body, so we could start there. And then we do the following random walk. So repeat the following. So you start here, let's say, select a random neighbor. So it has this point as neighbor, this point as neighbor, and so on, right? So in general, in n dimensions, a cube will have 2n neighbors. Select one of them uniformly at random, and then check if it's in the body or not by asking the membership oracle. If it's in the body, then you move there. If it's not in the body, then you again select a random neighbor and try where it is, whether it's in the body or not, and so on. So you could start like this and so on. You get to this point, and then you generate a random neighbor. Suppose it's this one, it's not in the body, so you're going to generate a random neighbor. And finally, you find a neighbor which is inside, and you move there, and so on. So you're doing this random walk. And a theorem here is that this random walk mixes fast, which means that after polynomial number of steps, polynomial in n steps, the point where you are is almost completely uniformly random in the body. You have generated a random point after polynomial number of steps. So I'm not going to prove this, but this uses the fact that convex bodies have no bottlenecks, which means this. So if you cut a convex body in any way, then you don't get a very small surface area, which could happen in a non-convex body like this, where you could cut the body into 2 big parts, but the surface area is very small. So if you were doing a random walk, then probability of going from here to here would be very small. So it will take long time to get to uniform distribution, which does not happen here because there's a good chance if you start from here that you will get here very fast. Okay, so that's the intuition. Okay, so all these things together, going to multiphase Monte Carlo and then using this random walk gives us the following theorem. So volume of convex body can be computed in time polynomial in n and 1 over epsilon within this approximation factor. So this was accomplished in a long line of work. The first algorithm, which is the generation of random points, which was the hard part, was done in 1987. And then there's a lot of work involving beautiful ideas. And the current best has runtime n to the 4. And there are several surveys on this problem. Okay, any questions? Okay, so I'm going to change gears now. So the volume problem motivates another problem, and which is where my some of my work is. Okay. So I'm going to talk about learning convex bodies. So we saw that we can compute the volume of a convex body efficiently. What else can we do? So we did this via generating random points in the body, which is a very useful primitive. So given that, you can do lots of things. You can compute the centroid, just generate some number of points, polynomial number of random points, and take their mean. And that empirical mean is a good estimate of the actual centroid. You can estimate other things like covariance matrix, surface area. So you can ask, can we learn the body itself? Okay. What does that mean? So here is one formalization of that. So suppose we are given a convex body K. It's either given via membership oracle, or it could also be given via random samples. So you're given some number of uniform random samples in the body. And we want to output a simple set S, which approximates K. What do I mean by approximation? It means that the volume of the symmetric difference is small relative to the volume of the body. By symmetric difference, I mean this. So if K is this input body, S is the set that we output, then the points which are in K but not in S, or points which are in S but not in K, they are in the symmetric difference. And we want this area to be small. then S will be a good approximation. Okay, so I don't necessarily require S to be a convex set. It just needs to be simple, so it should be computable in some easy way. For example, it could be computed by a polynomial or by a small circuit. There are such algorithms which output circuits to compute S. So S is just any set which is a good approximation of K. And so this is the problem. And this is a special case of problems which are studied in statistics and machine learning, which is density estimation or support estimation. So you have a probability distribution, you are given random samples from the distribution, and you want to know what the distribution is. Here our distribution is a very special kind of distribution, which is a convex body and uniform on that convex body, but it's in high dimensions. So the bad news is that in general this is not possible. We need 2 to the square root of n over epsilon samples to learn. So this is from 2009. And one can prove similar results for other settings, like the Gaussian distribution. So what I mean by this is that you generate random points according to the standard Gaussian distribution. For each point, you output a label, whether it's in the body or it's outside the body. So that's your input data. In our setting, we don't get any labels because all points are from the body. In this setting, you get a label whether a point is inside or outside, and then again, you want to output a set which is a good approximation. So here again, you get a similar lower bound.
In the previous result, it's uniform samples from the body?
Yes, that's the setting I'm going to be interested in. So I'm not going to go into the details of this, although it's not very hard. But I want to talk more about algorithms rather than lower bounds. So these lower bounds, they exploit the fact that there are convex bodies whose boundaries are very complex. And you have to learn that complex boundary in order to learn the body itself. And since it's complex, you have to make lots of queries. So you could ask what happens if the body is simple. Okay? So some simple bodies which intuitively seem to be simple are these. So you have a polytope in Rn with a polynomial number of vertices or a polynomial number of facets. In 2 dimensions, it's the sides. In higher dimensions, it's the n-1 dimensional face of the polytope. So I haven't really defined what a polytope is. Let me do that. A polytope is a bounded intersection of half spaces. Okay, so we saw this picture before. You have some half spaces, take the intersection. If it's bounded, then it's called a polytope. In general, it doesn't need to be bounded. So here again, we have an intersection of half spaces, but it's infinite in this direction. So in that case, it's called polyhedron. But we will be interested in polytopes, which are finite sets. So intersections of half spaces are very well studied concepts in learning theory. Perceptrons are just half spaces. Intersections of half spaces are closely related to threshold circuits and some versions of neural networks. So if you are learning polytopes, then it can be done actually if we have access to membership oracle. So that's interesting. But more interesting here turns out to be what happens if the points are chosen at random. So in our case, we are choosing points uniformly from the body. But there's also a study of the case like the one I talked about before. You choose random points from a distribution and see whether the point is inside or outside. You get labels for each point. So there's a lot of literature on this. And in that case, it's believed to be a hard problem in general. And the hardness comes from cryptographic hardness, not like NP hardness. And these hardness results use some very specially constructed distributions which are quite pathological, and you don't expect them to arise in practice. So it's more interesting to look at this problem for some nice distributions like Gaussian distribution or uniform from the body. And we'll look at this later model, which is uniform samples from the body, and the special cases, which is a special case of density estimation. Okay, so there was just some motivation for looking at this problem. Some more motivation will come later. So this is the problem we are interested in. We have a polytope which has polynomial number of facets. And we only get random samples from this polytope. We can't make membership queries. Can we output an approximation to this polytope? So now something interesting happens. So you can do this information theoretically, meaning that polynomial number of samples have enough information for you to get a good approximation. But to extract that information from these samples, we don't know how to do that. So there are no efficient algorithms to do it. Okay, so polynomial number of samples are enough, but we don't know how to learn the body efficiently in polynomial time. So this is not very hard to prove, but I'm not going to prove it. Instead, I'm going to move to this problem. So since we don't know how to learn general polytopes with poly and facets, can we learn specific polytopes? So some polytopes that we looked at before, like cubes or simplices, more generally parallelepipeds. Okay. I'm going to define what parallelepiped is a little later. So it turns out that you can learn these things, cubes and parallelepipeds. And I didn't know about this literature until recently, but there's a whole field of in signal processing called independent component analysis and blind source separation, with thousands of papers. Whose basic problem is basically this, for learning parallelepipeds, and lots of variations of that. And in recent work, we showed how to learn simplices. I'm only going to talk about this today. This uses similar high-level ideas, but it's more complicated. So I'm going to give you some intuition about how to learn cubes and parallelepipeds, and also talk a little bit about the relation to these areas in signal processing. Okay, so let me formally define the problem before we go ahead. So we are given polynomial number of random samples from an unknown parallelepiped P in Rn. By parallelepiped, I mean, I didn't write the formal definition, but it's just a linear transformation of a cube, or there are this intersection of half spaces where we have two parallel half spaces for each facet. So you intuitively get the idea of what it is. Okay. So we are given polynomial number of random samples from this parallelepiped, and we want to output a set S, which is a small symmetric difference from P. And ideally, S should be a parallelepiped here. It should not be some other kind of circuit or something, in order to be useful for the application. So this is the problem of learning parallelepipeds. Learning cubes is very similar. You are given polynomial number of random points from the cube, and you want to output an approximation, which should ideally be the cube itself. Should itself be a cube, not the original cube. So these problems are essentially equivalent. They are not very different from each other. And the problem is basically to learn the cube's orientation. So you can assume that the cube has a center at the origin, and we know its size, but the only thing that's hard to determine, to learn, is the orientation of the cube from the sample. So that's the core of the problem. So here, let me briefly talk about the relation of this problem with IC and BSS. And learning cubes looks a really cooked up problem. It looks very artificial, but it turns out that it's actually quite useful in many settings. So this is sort of a cooked up situation, but these fields are quite applied in biomedicine, in medical imaging, and in communication. These are quite useful techniques. So here, suppose you are in a party and you can overhear two people, and you are more interested in one gossip than the other. Can you tune out one person and tune into the more interesting conversation? So here is an idealization of the problem. The real world problem is much harder. We don't know how our ears work and how the signals are processed in our brain, but here is the idealization. So original signals are S1 and S2. Think of them as random variables. So at each time you can sample the random variable and get the value. So at each time instant you get a random sample for S1 and a random sample for S2. But you don't really get S1 and S2. What you get is a mixture of them because the two people are talking simultaneously. So in one ear you hear a linear combination of these two signals. In the other ear you hear this other linear combination. And so this is what you get at each time instance, the linear combination of these two signals, two different linear combinations. And so this is what you sample. And from this you want to recover the original signals. Okay. But now here, if you knew these coefficients, A11, A12, A21, A22, then it's just a system of linear equations. You can solve it because you're getting x1, x2, and you know these guys, then you can solve in S1 and S2. But here the interesting thing is that you don't know these numbers. A1, A's you don't know. So you don't know A's and you don't know S. And still you want to be able to recover S. That's the question. This question is basically the same as learning cubes or learning parallelepipeds. So if here I'm depicting these two signals, S1 is on the x-axis, S2 is on the y-axis. And since I'm assuming S1 and S2 are independent, right? The two people are talking independently. So because of that, we can think of this thing as a cube. And now we apply a linear transformation to this cube and we get a parallelepiped. So if we could figure out what this parallelepiped was, then we could get back this mapping, the linear transformation, and then we could get S1, S2. That's the general idea. So I'm going to now go back to parallelepiped problem. All right. So as I said before, the learning parallelepiped problem is basically comes down to learning cubes with the unit side lengths and center at the origin. And the only problem that's hard to solve is what the orientation is, how it is rotated in the space. So how can we solve this? Right? You have a randomly rotated cube in the space, you get random samples, and you want to know what's the orientation of that cube. So one simple approach could be that you find the smallest volume cube that contains all the samples. All right, and this is actually the good cube. This will be the right fit. But it turns out to be hard to do. So you can do it again in constant dimensions like 2, but in general it's a hard problem. It's NP hard. But the hardness comes from assuming that these things are not random. You are given some sample of some points, some set of points, and you want to find a cube that's the smallest volume and contains all of these things. So that's a hard problem. But in our case, we are getting random samples, uniform random samples from the cube, which is not a general set of input. And here this hardness result won't apply, but we still don't know how to do this efficiently, how to find the smallest volume cube. But something similar works. Okay. So here's the idea. We look at the fourth moment of the input cube in direction v. So v is some vector in Rn with length 1, so like this. And let's say the cube is like this. It's axis parallel just for the moment. Its sides have unit length. So then by the fourth moment, I mean this. You take every point, look at its projection on V, raise it to the fourth power, and take the expectation. So this is over all points x and q. Okay. And this turns out to a very simple expression. So if the input cube is x is parallel like this, then the fourth moment is just some constant c1 minus another constant c2 times the sum of the fourth powers of the v's. Okay, let me show you quickly how this comes about. So what we are doing is this. We take the dot product between v and x, this dot product, which is just v1 x1 plus v2 x2 and so on. We raise it to the fourth power, and we take the expectation. So when you open this thing using multinomial theorem, then what you get is vi to the 4, and the expectation of xi to the 4, plus some constant, and then the sum over I not equal to j, vi vj cubed, and the expectation of xi xj cubed. But this thing is 0 because xi have 0 expectation, xj's cube is again will have 0 expectation. These two things are independent. Xi and xj are independent. So all of these things will become 0. So what will remain is just this original sum and this other sum. Sum over I not equal to j, vi squared vj squared, expectation of xi squared xj squared. Because it's both of the powers are even, so this doesn't become 0. And when you simplify this a little bit more, then you get this expression. So this is very simple, right? Why am I not looking at, excuse me? Okay, so that was the fourth moment. Sorry, I forgot to show you one thing. So you can plot this here. So this is the fourth moment. It looks like this. Okay, just plotting this function. Now here I assume that the cube is x is parallel, but of course our problem is to find the orientation when it's not x is parallel, it's in some general position. But now the fourth moment just behaves the same way. If you rotate the cube, then the fourth moment will also rotate the same way. Right, that's obvious. So if you knew this fourth moment function, if you knew this thing, then we could try to find the orientation of the cube by doing some optimization on this. So we could try to find the local optima of this function. Right, the local minima are these 4 points, and they exactly correspond to the facets. Right. So if we knew this fourth moment, then we can hopefully find the orientation. And we actually get a good estimate of the fourth moment from the sample. Right. The fourth moment is this, but what we have is these random samples, polynomially many random samples. We just take the average of v dot x for x in the sample, and that's a good approximation of the fourth moment in all directions v. So g of v is a good approximation of f of v. So we get this thing approximately. And so our problem now is to find local minima over degree 4 polynomial on a sphere. So in general, it's a hard problem. Number of local maxima or minima can be very large. It can be exponential. But in our case, local minima precisely correspond to the facets, which are just 2n in number, and they can be found efficiently using a gradient descent kind of algorithm. So that's it. So you can find the orientation of the cube by finding the fourth moment and then using gradient descent to find the local minima of this function. I'm not going to go into the details of how this is done. Okay, so this is the last slide. So we still don't know how to learn polytopes with polynomial number of facets in polynomial time. and learn parallel pipets when there is noise. So points are perturbed by some noise. All right, that's it. Thank you.
Maybe I misunderstood your statement, but in the previous slide, the function we tried to minimize, we can only approximate these
Yes.
two samples, right?
Right.
So then the approximate function should still have the...
Yeah, so you have to show that even the gradient of, you can approximate the gradient as well from the sample.
So you could still have the same number of local minimums?
Yes.
So in the case of the simpler bodies like parallel or synthesis, if your body is a union of finitely many such shapes, can you extend the regression?
If it's a disjoint union, then I think you can, probably. I mean, if they are far from each other, then you can. But in general, I don't know. It's not clear at all.
Thank you.